Recall that this symbol R2 denotes the Cartesian cross product of the set R with itself. Now for x and y real numbers, we define a map D from R2, the set of all ordered pairs, into the set which is the semi-infinite closed interval, an unbounded interval, as follows. D of x comma y equals the absolute value of x minus y. For example, D of 7 comma 2 is the absolute value of 7 minus 2, which is 5. D of 5 comma negative 3 is the absolute value of 5 minus negative 3, which is positive 8. And D of negative 4 comma 9 is 13. This map D is called the Euclidean distance between the real numbers x and y. For example, the distance between the real numbers 5 and negative 3 is positive 8 on the real number line. We observe that the map D has the following properties. Property 1. D of x comma y is greater or equal to 0 for all real numbers x and y. This property is called non-negativity. Property 2. D of x comma y equals 0 if and only if x equals to y for all real numbers x and y. This property is called definiteness. In other words, the distance between two real numbers, if it is equals to 0, then the numbers x and y must be the same. Conversely, if two real numbers x and y are same, then their distance between them must be equal to 0. Property 3. D of x comma y is equal to D of y comma x for all real numbers x and y. This property is called the symmetry property. Property 4. D of x comma y is smaller or equal to D of x comma z plus D of z comma y for all real numbers x, y, and z. This is called the triangle inequality. Let's see the proof of these properties. The proof of the property 1 follows directly from the fact that absolute value of any real number is non-negative. The proof of property 2 follows directly from the fact that absolute value of a real number x equals to 0 if and only if the real number itself equals to 0. The proof of property 3 follows from the theorem 5.1.1, the statement A. And the proof of the statement 4 follows from the corollary A of the theorem 5.1.2. Now, we are going to define a map on an arbitrary set X into the non-negative real numbers. This map is called a matrix. Let's have a look at the formal definition of a matrix. Let X be a non-empty set. A map D from x cross x into the set of non-negative real numbers is called a matrix on X if it satisfies the following properties. Property 1. D of x comma y is non-negative for all x and y in X, which is called the non-negativity. Property 2. D of x comma y equals to 0 if and only if x equals to y for all x and y in X. This is called the definiteness property of the map. Property 3. D of x comma y equals to d of y comma x for all x and y in X. This is known as the symmetry property of the map. The last property, d of x comma y is smaller or equal to d of x comma z plus d of z comma y for all x, y, and z in the set X. This is called the triangle property of the map D. The set X together with the map D or the matrix D is called a matrix space. In other words, the pair X and D is called a matrix space. For example, the map D from R2 space to the set of non-negative real numbers defined by this formula is a matrix since it satisfies all those four properties as we found earlier. This matrix is known as the standard or Euclidean matrix, and the pair R comma D or R comma the absolute value map is called the matrix space, also known as the Euclidean matrix space or simply Euclidean space. Let's have a look at a different example of a matrix space. Let X be any non-empty set, and we define a map or a function from x cross x to the set of non-negative real numbers by this formula, which says d of x comma y is 0 if x is equal to y, or d of x comma y equals to 1 if x is not equal to y. Then we can show this map is a matrix, and the set X together with the map is called a discrete matrix space. For convenience, we often write X as a matrix space. But we should keep in our mind that there should be some matrix lurking behind our discussion. Let's see the proof of whether D is a matrix. The first property is called the non-negativity. We should prove that for all x and y in the set X, we have d of x comma y is non-negative. And this is clear from the very definition of the map itself. Because if x and y is in the set X, then the d or the distance between the x and y must be either equal to 0 or 1, which is non-negative in every case. Property 2, definiteness. If x equals y, then d of x comma x equals 0 by the definition of the map D. Conversely, if d of x comma y equals 0, then by definition x must be equals to y. Therefore, d of x comma y equals 0 implies or implied by x equals y. Property 3. If x equals y, then d of yx equals 0 which is equals to d of x comma y. And if x is not equals to y, then d of y comma x equals 1, which is also equal to d of x comma y. Therefore, for all x, y in the set X, d of y comma x equals d of x comma y. So the property 3 is satisfied. Similarly, we can try to prove the triangle inequality property of the metric we defined earlier. Please pause the video and have a look at the proof, or see the notes for the details.